Thank you, Maxim. First, we'll wrap up the previous lecture to finish with modern solutions and modern results. Okay. So we've discussed the ways to improve rendering and training speed, but still those algorithms mostly apply to synthetic data, and they do not really perform well on real-world scenes you would want to capture. And there are a couple other tricks that are essential that were developed in previous 3 years. And the first one, which is a very common issue in computer graphics and in signal processing, is that those rendering algorithms, they exhibit an effect which is called aliasing. So aliasing is an overused term which represents effects that arise when you try to represent continuous signals with a discrete set of measurements. And these two pictures illustrate the effect of aliasing we're going to encounter in nerves. What is the effect? So the pixels on our image are pixels displayed on our monitors, and they have physical size. They cover some areas of 3D space with a shape that may look like a cone. And if we were to depict a checkerboard, like on this picture, the pixels that are close, that represent areas of checkerboard that are close to the camera, they cover only segments that have constant colors, because relative size of the pixel to the segment projection works in our favor. The pixel only covers the area of constant color. But as we move further and further from the camera, we start encountering pixels that cover segments that both contain white pieces of checkerboard and black pieces of checkerboard. And recall that our algorithm used to compute pixel color, assume that our pixel color comes from an infinitely thin ray. And this ray, by design, passes through the center of a pixel. And for a pixel that is far, that covers an area far from the camera, it can randomly encounter either a black area of checkerboard or a gray area of a checkerboard. Since the pattern is regular, the lattice of pixel is regular, we see some strange patterns that do not exist in real life. We do not see such patterns in real life, but they happen with images. So the term aliasing comes from the idea that high-frequency pieces of our images, so regions where color changes at really high pace due to small size of checkerboard, they arise as they work as an alias, and the aliases, they represent themselves as lower frequency signals. Like this part, this part of the checkerboard looks like it's supposed to be here, not there. And the frequency of the change of color is not the way it's supposed to be. And the solution here, the best solution that would be possible, that would be ideal, is to compute pixel colors in a different way. So our pixel covers a certain area of an image. We could have, instead of using the center point in a pixel, sampled several points in the pixel and return an average color of those points in the pixel and depict an average color. So those distant pieces of checkerboard, they both have black pieces, white pieces, and they end up being gray. And these areas, they gradually turn gray as the scale diminishes. Well, but the picture on the right is not our ideal solution because remember that we had issues with wasting too much compute on getting single pixel color. Computing multiple colors per pixel is not possible because it will ruin the performance of a simple system. And the classic solution in computer graphics is to pre-compute the size of, pre-compute the textures for different scales. For example, if we see the checkerboard near the camera, we would use this texture and use it here. But if we look at the checkerboard in far, far away distance, we would use not an average pixel color, but we would use a texture which has been downsampled with average pool several times. And average pooling would also turn this texture gray and would work as good, almost as good, as an exact ideal solution. So the authors of the original NERF paper, several years after the original publication, they noticed this issue in the original work. And I want to underline that the data that I've shown you before is actually biased, because the synthetic data, it only consists of cameras flying around at a fixed distance from an object. We do not change the distance to an object, and this is a situation where we could encounter these change of scale, which could have led to aliasing effects. And when the authors change the distance in their training set, they indeed encounter aliasing effects in the model they've restored. Okay, so in computer graphics, they tend to use this solution called MIP-map, where you store a texture along with downsampled copies of texture. But this solution would not be feasible for neural networks. And the authors proposed a similar solution. So they proposed to modify their architecture a little bit. So as I mentioned before, a pixel on an image covers some area of a display. So they took into account the size of an area covered by a pixel, and the size of this area gradually increases as we go further away from the camera. And instead of plugging in just a single positional argument, they also took into account the scale at this position and plugged it in as a second argument. There's a smart architecture for this to output density and color with respect to scale parameter. We'll not go into details of this solution, but this solution solves an issue with aliasing in NERFs, and it allows to improve rendering quality significantly. Okay, and another issue is that in the data I've shown you, there's another bias, another hidden bias, is that we do not really care where is the bound of an image. Synthetic data, for synthetic data, we knew that background is white, and we could have stopped rendering at certain distance and not go far beyond, as we would have in real data where we have to encounter horizon. The second data set with feed-forward cameras, with forward-facing cameras, it captured real-world scenes, but due to nature of the data set, all the distances in the image were limited to reasonable distances. So when the authors took positions on the array, they could have clipped sampling array positions at a certain point. But in real life, you would want to sample array positions until infinity, because scenes are often unbounded. And a pretty simple solution here was to map 3D space into a ball, which has finite size, and process the ball just as a scene of a finite size. So the mapping worked like this. You select a region of a scene which is the core, which is the central scene you want to represent. And then you map all the remaining parts of your 3D space into a shell around the central part of a scene. Mapping is pretty simple. It's like identical mapping in the center and inverse mapping, like hyperbola, outside of the center. And this allows to process scenes that are unbounded. There were several improvements down the line, but after all, those two solutions allowed working with real-world scenes, and this culminated in a paper called ZipNerf, which was published on Archive this spring, which combined the two approaches we've discussed so far. So there was a line of research improving rendering speed, which culminated in instant NERF architectures, instant NGP architectures with hash grids. And there was a line of research which culminated in a model called MIP, NERF 360, MIP for this anti-aliasing technique, and 360 for 360 unbounded scenes. And the combination of those two approaches and resulted in a work called ZipNerf. ZipNerf adopted architectural solutions from MIPNerf to instant NGP and combined into rendering technique that looks like this. So this video is rendered by a bunch of neural networks. You can spot some issues in reflections because the reflections are hard to reconstruct, but overall rendering is quite good. Okay, that's all for improving fidelity and speed. I would like to provide some further references if you would want to work with nerves. So, sparsification technique and solutions for rendering speed are quite complex and they require custom code on CUDA. But it's already implemented in a nice framework which is called Nerve Studio. You can check it out if you have a desktop computer with a GPU, maybe a laptop with a GPU. You can install this package and use your own data to reconstruct scenes from your life. Also, this technology is being implemented in several practical solutions. For example, there's an app called Luma, which is available for example, iPhones, which allows you to capture a video and then send it to a cloud to the Luma team. They process the data automatically and return you a 3D model with nice visualization features and all this stuff. By the way, these days you can render previews real time, and even Nerve Studio has a nice real-time preview feature. Okay, and there are several topics which are also which also deserve attention, but we don't have time for them. For example, nerves, they also apply to video. And there's a nice paper on reconstructing dynamic video sequences for image stabilization and novel view synthesis. For example, Dynibar and many other papers. I've mentioned before that it is not necessary to obtain high-quality surface reconstruction in order to be able to solve novel view synthesis. But there are efforts in order to improve not view synthesis quality, but surface reconstruction quality. These efforts involve additional regularization techniques, and this line of research culminated this summer in a paper by NVIDIA called Neural Angela. And also there's a rival approach, which is not at all related to volumetric rendering, but it solves novel view synthesis with a point cloud related technique. You can check it out on this nice website. This is not a reference to paper, but this is a reference to a website that implements this solution. You can go there, click on a scene, and view it on your phone, which is pretty impressive from my point of view. So that's it for the first presentation. Now we can proceed to the second. Are there any questions regarding the first part, maybe? Okay, then I will happily proceed to the second part. So in the second part, I want to leverage the machinery we've discussed so far, along with text-to-image generative models, in order to generate 3D assets and 3D scenes. And again, I will start with a few motivational examples. First one is on the practical side. So these days, 3D assets, they are in demand. For example, computer games are quite popular, and as people strive for higher quality content, the costs of developing a computer game keep rising. I have a picture from a presentation by Andrew Price on AI in computer industry. And this picture is a motivational picture covering the costs of development of different models in a computer game. I guess these are approximate costs, but so the development of hero characters is $50,000 because you have to develop a nice model which can be animated and so on, like a huge amount of money. But maybe it is worth it to design a beautiful hero which you can relate to. Well, okay, but also next to the hero there is a barrel, a rusty barrel, which nobody cares about. But in this image, this rusty barrel has a price tag of nearly $1,000, and it seems completely unreasonable to waste such amount of money and effort on developing game assets that nobody will care about. And there's a hope that machine learning technology and generative modeling will be able to provide us with cheaper 3D assets for games, for simulation for robotics. So this is a practical motivation. Another motivation for listening to this talk is on the conceptual side, because the technique we're going to talk about is not limited to 3D game assets. So I think the technique we're going to talk about is pretty fundamental and can be applied far beyond the framework we're discussing today. So in many real-world applications, you tend to encounter so-called inverse problems, where you have some set of indirect measurements, and you want to recover the parameters of the system that led to these indirect measurements. Recall the previous lecture. So we were working on novel view synthesis. So our measurements in this case were pictures taken from a known camera pose. Camera pose varies, so camera pose is ZI. It leads to picture XI, and the parameters, the shape of a scene we want to reconstruct is here represented as theta. So we want to reconstruct theta, but we only can look at the pictures of a scene, not we cannot touch it or do some more complicated measurements. This is a funny example, but it stops being funny when you talk about not measuring 3D scenes, but measuring people internals of patients in hospitals. For example, with MRI machines, you measure magnetic fields somewhere near the person, and with these magnetic fields, you are able to investigate the internals of a person, investigate how their organs are developing without opening the person, without accessing the person directly. So these problems are pretty important. But here we have a direct correspondence between our observation and the observation setup. For example, camera location, magnetic field parameters. But in the applications we're going to talk about today, we're going to move away from this direct correspondence. We'll work with a generative model which captures some general notion of how our data can look like. And with this generative model, we want to find theta that can lead to plausible samples, but without any direct correspondence to camera parameters and so on and so on. This may sound complicated, so let me rephrase it in a very concrete example. So imagine you have a generative model which is trying to make pictures of cats. You only have a generative model that knows how a picture of a cat looks like. But we want to find such theta, a 3D model of a cat, that for given camera parameters Zi, we, with our rendering algorithm G, obtain plausible images of a cat. Plausible maybe in terms of our generative model, so our generative model sees an image that we've rendered and says, well, yeah, this is a cat. I've seen some cats, this is a cat. So the technique we're going to talk about does something like this, but the technique is in its early stages of development, so I cannot really make the definition more formal. So I'm sorry for being a little hand-wavy, but this is a motivational slide after all. So this setup we're going to talk about, it's limited only to text to 3D without any more complicated data. So we're given a pre-trained diffusion model that takes a text prompt and generates an image. We're given a text prompt which captures information about the thing we're trying to generate. And with those two pieces, we want to produce a 3D model. Okay. For example, we have a diffusion model. In this example, diffusion model was imagined by Google. We have a prompt saying that we want a nice photo of a squirrel reading a book. And here's the squirrel we can obtain with this technique. So it looks pretty convincing, a little cartoonish, but clearly it's a squirrel. Clearly it's wearing kimono, and clearly it's reading a book, just as we asked our model to generate. So quick recap for people who were absent on the first lecture, we're going to represent 3D scenes with neural fields that consists of two parts, a density field and a radiance field that represents the color. But this time, radiance field will be simpler. So in the first talk, we were trying to reconstruct data that we encounter in real life. And our radiance model should have taken into account real-life lighting effects, such as dependence on view angle. Here, we're free to choose what kind of model we generate. And here we say that the color of position does not really depend on view angle. It simplifies learning and makes a model a little bit lighter. Again, we will use some sort of architectures. We can use MLPs or hash grid functions. It does not really matter. And with those representations, we run a rendering algorithm that casts rays in a pinhole model. And for each rays, it computes density and color along the ray and combines these quantities with an alpha compositing algorithm. I'll have letter alpha. I'll use letter alpha for different variables. So here I do not write alpha. I write explicitly exponent minus sigma. Okay, and this is a video of how training looks yet again. This is it for neural radiance fields, and now a quick recap of the details that comprise a diffusion model modern. So what is a generative diffusion model? So essentially, when you download a diffusion model, you end up with some sort of UNet that takes an image as an input and produces some sort of an image as an output. But what are the inputs and what are the outputs? The idea behind diffusion models is that you collect a data set of nice-looking pictures you want to model, and then you define a fixed process that corrupts these images and turns them into white noise. And this process is fixed, and it maps our image data set into a set of random noisy variables. And the UNet you work with is a special neural network which is trained to essentially invert this process. It takes a noisy image as an input. It takes some data about how much noise do we have, and it tries to reconstruct the image we started with. So the corruption process looks like this. The corruption process is on the top of the slide. At time step t, the corrupted image is a sum of uncorrupted image with weight alpha t. Alpha is a weight corresponding to time, and x0 is our clean image. And the second term is a sum of Gaussian noise, standard Gaussian noise, scaled with another parameter sigma t. Our UNet essentially tries to predict what was the noise that was added to an image. And in order to approximate the original image, you can compute this expression, which takes noisy image, takes our guess what the noise was, multiplies it by the same scale, subtracts the noise term. We end up with an approximation for alpha t x0, and then we divide by alpha t. So this is how UNet can be used to reconstruct the original image. And there are several important facts about diffusion models that I'm not able to cover in detail, but we will have to keep them in mind. So essentially, our diffusion process defines a set of random variables. So when we do not add any noise, we can consider our random images from the data set as a random variable. With some sort of data distribution, we want to recover during our generative modeling. Then for each time step t, which is a discrete set of steps, we introduce another distribution which models the distributions of random images with random noise on top of them. I will denote this distribution as PT, with P0 being the distribution of our training set, of our training data, or just empirical distribution, and PT denoting with T being greater than 0, distribution of noisy images, random image with some random noise. And the fact we have to remember for this lecture is that, well, the UNet is not only a magical machine which predicts what was the noisy component of an image, it also models so-called score function of our distribution. So if we have, if our distribution has density PT, we can compute log density and then compute the gradient of this density. This is quite common in statistics, in machine learning, and this function is called score function. And it turns out that our UNet with a proper scalar parameter approximate the score function of our noisy distribution. This fact will be important for the motivation of the method I will present. Okay, so what's the idea? What could be the solution behind an algorithm that generates 3D scenes based on text prompts? Well, another important fact about diffusion models is that the loss function that they optimize can be seen as an estimate of a likelihood of an image. So if we have a corrupted rubbish image, we could have computed the likelihood of this image and optimized the likelihood with respect to input image in order to produce better image. So during training of diffusion models, we usually tune the parameters of neural network in order to obtain nice density approximation for our data. But this time I'm proposing to reverse this process, and instead of tuning network parameters, I propose to optimize the loss function of a diffusion model with respect to image we want to generate, but not with respect to parameters. And in this setup, the parameters are fixed, and we use a likelihood function obtained through diffusion model as a training signal propagated to images we're trying to estimate using the likelihood function. So idea is conceptually on the surface. Machine learning has a long history of designing loss functions as some variants of likelihood functions for optimization. Here, the likelihood is defined over images, and we want to optimize the likelihood over argument to get a nice image. And so the idea is to take the loss of diffusion model and optimize the loss with respect to images we produce. So how do we produce an image? Recall that we have a nerve model that takes a parameter theta. This time the parameter theta represents density and color. It takes camera, which I will represent as Z, and renders scene from viewpoint Z, and generate image X. So we have a loss function for our diffusion model, and we want to optimize the loss function over various viewpoints of our scene. We sample different camera views Z, and we optimize average loss over different images at different viewpoints Z. So this is an idea. Does it work in practice? Let's dive into details. The loss function I was talking about is pretty simple. It looks like mean squared error between UNet and the noise sample we are trying to estimate. It's weighted with respect to weights that are different for each time step, for each granularity of noise. And let's plug into this loss function our expression for the image on the second line. So here we have xt, which is x with some additional noise. So we take x0 and add noise and add additional weights in order to obtain proper random variable. And we can compute the gradient of our loss function with respect to parameters that generate our scene. Well, usually when you design some machine learning algorithm these days, you do not compute the gradients. And the fact that I'm computing gradients should feel strange. Well, in fact, the gradients we're going to use are not the gradients that I have proposed in this approach, because if you were to try to train a model with this approach, with our estimate of likelihood being optimized over model parameters, you would fail. It does not really work in practice, and there's a tiny little hack, which on the one hand speeds up training. It's very convenient. And on the other hand, it makes an algorithm which is nice conceptually and doesn't work. It turns it into an algorithm which is nice conceptually and works in practice. And is also pretty robust. So what is the nice trick? The nice trick is to omit one of the terms in the gradients. Let's look at the gradients a little closer. So when we differentiate the mean squared error, we end up with a difference. And then we differentiate our UNet with respect to its arguments, and then we differentiate the arguments with respect to its arguments, and end up with expression containing the Jacobian of UNet, epsilon with hat, the Jacobian of noised image with respect to original image, and the Jacobian of our rendering algorithm. In this formula, one of the heaviest parts is the Jacobian of UNet. To compute this Jacobian, we have to store temporal activation of a UNet, which involves some memory limitations. But if we do not compute the Jacobian, we can compute these gradients without storing activations of UNet, which is very nice. Let's check this. We can render an image without storing activations of UNet. We can compute this gradient without storing activations. And in the difference term, we do not have any gradients of UNet with respect to anything. So in order to compute this loss, we can use our diffusion model in inference mode, but not in evaluation mode, which is very nice. It's faster, it requires less memory, and it works. But why? So I will spend next several slides trying to convince you that this trick, which may look heuristic, in fact has some intuition behind it. So in the paper that presented Dream Fusion, the text-to-3D rendering approach, the explanation for their setup they presented in the main part went like this. We compute the gradient, omit one of the terms, it works, hooray. But there's a deeper intuition behind this. So let's start with our gradient and try to infer what is the function that leads to such gradient. So what kind of laws would lead to this exact gradient? Okay, so here I wrote down the gradient we use for training without the Jacobian. And I'm trying to transform this gradient to get some insight. So first of all, we see that we compute the expectation with respect to different time steps for different levels of noise. We compute the expectation with respect to different noise samples, and we can switch the order of expectations. Well, WT does not depend on epsilon. These gradients do not depend on epsilon. The only thing that depends on epsilon is this this bracket. And the noise distribution we have is known in advance. It's a standard Gaussian distribution. So the average value of this term is essentially the average value of our diffusion U-net with respect to input noised with value epsilon. And this is it. So on this slide, I've simplified the expression for the gradient by a little bit by getting rid of the explicit noise term in the formula. Can we do something else to simplify the expression? Well, indeed we can. Let's look closer at what the expectation of our U-net with respect to epsilon is in practice. Several slides ago, I told you that the ultimate goal of training diffusion model is not modeling pictures, but approximating the score function, which is the gradient of our distribution noise to time step t with respect to argument xt. So if we're confident that our U-net is trained properly, then we can assume that our U-net essentially approximates an expression that looks like this. It's minus sigma times the score function of pt. Okay. And with this in mind, we can rewrite the average of epsilon hat as the average of score function and can plug it into the expression we obtained on the previous term. So this is an average over different time steps with different weights of an expression which is, after the substitution, reminiscent of chain rule. And indeed, we take the score function of xt, and the other terms is xt Jacobian with respect to x0 and g Jacobian with respect to theta. And those three components can be aggregated into a single gradient of our density pt with respect to theta, but the average is taken with respect to different samples at different time steps t. Okay, why is this average more intuitive than the approach we started with? I'm sorry. I hope that the next slide will provide some intuition, which will make the method more intuitive. So the original approach we're trying to develop was to optimize an estimate for the likelihood of an image. And the approach we're taking right now is to optimize the likelihood of image with taken at different noise levels. Why is it a better idea? So whenever you train a diffusion model at some noise level, you plug in the noise samples that you obtain at this noise level. For example, when you train a UNet at noise level 0, you plug in only clean images. So imagine that the images are on some manifold, which can be drawn on a plane as those two moons. So you plug in only clean, nice samples, and these are the only samples that the model is familiar with. And for the points outside of those two half moons, the predictions of UNet are arbitrary. They are noisy. UNet is not trained on these points. But as we progress, as we add more noise, the data points that UNet is trained on cover more and more space, ending up with the whole space with white noise. So when you optimize the points with higher noise rate, you use a UNet at locations it saw during training. So imagine you start training a scene that produces an image, clean image, that is right here. The gradient that is obtained from a UNet right here is arbitrary. It does not lead you to high density areas because UNet was not trained there. And training starting from drawing picture starting from this point will not lead us to those regions. But, however, if we simultaneously optimize images at all noise levels, we can start with a meaningful gradient at higher noise levels because UNet is able to process all noisy images because it saw many noisy images during training and it generalizes. And during training, the second approach starts with meaningful gradients at higher noise levels. And then as you gradually converge towards the two manifolds we want to end up on, your gradients with lesser noise components start contributing to improve your rendering quality. So this averaging with respect to different noise levels ends up being a more robust optimization procedure that can produce an image starting with an arbitrary input point, but not with an input point on an image manifold. Okay. That's it for the discussion of the loss. Let's proceed to the training visualizations. So how does the training work? It's not really complicated. So you choose a prompt before training the model. You initialize a diffusion model, and then the training loops the training loop is essentially a step where you sample a camera position, maybe several camera positions in a batch, render image, maybe several images. Then you sample noise level for your objective. And then given the noise level and the rendered image, you estimate the gradient with a Monte Carlo estimate for T and epsilon. And update theta that parameterizes the 3D scene with R gradient. And this thing tends to work in practice. And here's a video demo of how it works, how training works. This is a bunny located on top of pancakes. Camera position is fixed. And just as before, you start with an approximation, almost transparent ball with no bunny, and during training you gradually converge to nicely looking 3D model of a bunny. But in fact there are several caveats, several tricks that I didn't mention yet, and in the rest of talk I will tell you about practical tricks that improve rendering quality, because this approach works, but not as good as it could with additional heuristics. So what problems do we encounter during this training? Well, first of all, there is no free lunch, and the model that is trained on 2D data is hard to trick into generating 3D data. And a naive, silly solution to the problem that we've posed is to output something planar that depicts the thing you've asked in prompt, and to repeat this thing from different angles. And this is the configuration that the algorithm finds on the left. So here it tried to depict a bulldog with a pirate hat, and during training it found the model of a bulldog that had two faces, from one angle and from the second angle. From the viewpoint of diffusion model that produces our training signal, this model is fine. It has a bulldog on it, it has a bulldog on it, from different angles, great. But from the viewpoint of practitioners, from people who want nice 3D assets, this is rubbish. But there are simple solutions to this problem. So the most naive and pretty effective solution is to augment our prompts. So we can specify what kind of dock we want. We can specify camera positions, the angle of camera that we're using while generating an image. For example, we can say dock with a pirate hat view from above, front view, side view. And these prompt augmentations tend to help and allow you to move from the model on the left to the model on the right. However, the model looks convincing, but the geometry of a model is not very good, because you can see that it's not smooth, it's pretty chaotic. And if we apply some shadowing algorithms from computer graphics to the surface that we've obtained, the output will be horrible due to surface artifacts. Can we fix this? Well, yeah, we can train not only images that are model produced, but images with additional shading details, and maybe not just images with shading details, but images without textures, with pure shades. The second heuristic was to add images that are shaded with the simplest Lambertian shading algorithm that you may have encountered in school in some form, and augment training data with surfaces with shades without any texture or color. Because, well, you can see that this is a dog with a pirate head, sort of pirate head, even without colors. With those augmentations, the authors improved their results even further and obtained an image that looked like this. So shadows look nice, but there's still an issue that instead of drawing a skull as a texture, it imprinted a skull as a part of 3D model. But overall, the model on the right is much better than the model we start with two faces and chaotic details, which is nice. But there are still problems. There are still problems to fix in this model. There are several of them. First of all, poor model quality. The models that we have seen so far are cartoonish. They seem low resolution. They do not look realistic. However, practitioners, I guess, would prefer realistic assets rather than cartoonish assets most of the time. The objective is seemingly ad hoc. How do we average times? Why do we average times? I hope that the derivation I provided convinced you a little bit, but there are hyperparameters in this procedure that at this point seem arbitrary. Okay. Another problem that you could encounter while running this model in practice is a low sample diversity. For a single prompt, this model tends to end up producing almost the same model for different seeds. And this is not the kind of sampling we want from good generative models. And there are ways to fix this, nice out-of-box thinking ways to fix this. And there's still the Janus problem. Even with all those improvements, often for some seeds, we end up having models that have several faces that look horrible. We can fix all these problems with most of these problems with nice engineering approaches. How can we do this? Well, first of all, let's discuss model quality. The first work, diffusion on text 3D, which produced nice coherent 3D models, was presented by Google with their model called Imagine, which is a cascade model that first generates images on scale 64 by 64, then images on higher scale, and so on and so on. But the authors of Dream Fusion paper, they ended up training model only on an architecture which is trained on images of size 64 by 64. This resolution is quite low, but nevertheless it leads to coherent models. But at the same time, broader public doesn't have access to Imagine. It cannot even reproduce the results. But there is a model called Stable Diffusion, which works at higher resolutions, like 500 by 500. And those high resolutions can provide with finer training signals than training signals that you obtain from a diffusion model trained on low 64 by 64 resolutions. So it turns out that almost without any tricks, you can adapt the loss that we've discussed so far to latent diffusion models, namely stable diffusion that encodes an image and then runs diffusion in latent space in low resolution. But effectively, after the adaptation, the loss function generates training signals for images of resolution 500 by 500. And it turns out that training on better resolution with better parameters can significantly improve render quality. So as an illustration, I took an image of ablation study from one of the recent text 3D papers. This is on the left a picture of a skull trained on a 64 by 64 diffusion. And these are, on the right, these are several improvements over low resolution model. So the first improvement is just moving on from low resolution to high resolution. And even with this single improvement, you can see that the shape, the edges of the model that you produce improve significantly. Here we have nicely defined edges, whereas the edges of the low resolution model, they were blurred due to low resolution training signals. We can even improve the approach further with smarter averaging for different time scales, and we can improve the loss even further. We'll talk about the third component in a moment, but we'll not talk about the fourth improvement due to time limitations. Okay, so few slides ago, I was talking about the importance of computing gradients of UNet used in diffusion at different noise levels. Because at higher noise levels, you obtain meaningful training signals after initialization, but at lower noise levels, you obtain meaningful gradients near the convergence of the model. And apart from my hand-wavy arguments, I want to present a picture from a work that conducted a careful experiment trying to depict how training of text-to-3D model looks like. So on axis X, we have the same model at different stages of the training procedure. This is the model after initialization, and this is just a gray blob on a gray background. And after training, we end up with a tiny model of Spider-Man. How do the gradients look like? So the answer to this question is visualized below. At axis Y, we depict different noise levels, with 1 being the least noisy image, and 1000 being the most noisy image. So the gradient after initialization at level 1000 leads you toward some human shape without any details. But the gradient at level 1 is just some sort of noisy image with a spherical shape that is produced by our initialization, which has no semantic meaning. And as we proceed and train model, we gradually start obtaining meaningful gradients for finer details. And the gradients for lower noise levels start being useful. So here, the shape of Spider-Man is more nuanced. Here we are trying to correct the texture of a model, but not the background. And here the gradients of texture have biggest amplitude, and background is just modified a little bit. So it makes sense to start training with higher noise levels and then finish training as you converge with lower noise levels. And in fact, most modern solutions for text-to-3D train their models in 2 steps. The first stage works in high noise regime, and the second stage works in low noise regime. Okay. So these are some fixes to the arbitrary training procedure, to arbitrary hyperparameters that we have to somehow choose weights and training times. This is I've also presented a solution to low quality due to low resolution. Now we'll talk about tackling low sample diversity a little. So low sample diversity is in fact not very surprising, because during training we're trying to find an image which has the highest likelihood. And as a result, we end up getting stuck in modes of the distribution with the most common visualization of the thing that we've asked in the prompt. And probably we cannot fix this issue without resorting to a different training procedure that does not start with optimizing likelihood. But we can tackle low sample diversity in a completely different manner. So for diffusion models in the recent years, there were various modifications were developed. For example, there were algorithms like photo booth, text inversion, and all those things that allow you to generate not an arbitrary image, but an image of a model you wanted to obtain at first hand. For example, if you want to obtain images of this dog in different situations, you can plug in several pictures of a dog, even up to a single image, and run diffusion model with slight modification to obtain images of the same dog that you've given as an input to obtain images of a dog. Okay, we can take a model that is specifically modified to produce various images of a single dog to generate 3D model of a dog. And we can augment the prompts with different aspects of what kind of dog we want to generate in different scenarios: sitting, sleeping, or jumping. And with those inversion algorithms and prompt augmentations, we can sort of solve the problem of low sample diversity. And the models we've obtained here, the authors of the paper obtained here, they do resemble the original image, which is pretty cool. So this is a solution to low sample diversity, and the other problem I want to discuss is the Janus problem, the fact that the algorithm aims to be lazy and depict the same flat image from different angles and sell it to us as a coherent 3D model, which is unsatisfactory. Well, there are various modifications of diffusion algorithms being developed, and in a work called 0123, the authors proposed to fine-tune a diffusion model so that it could produce the image of the model we've given as input, but from different view angle with a fine control over the angle. So how could you do this? Well, you can collect some 3D data. You don't need a lot of 3D data to fine-tune a model, and you can render those collected models from different viewpoints and collect a data set of a canonical view of the model, of a translation angle you want to model, you want to emulate, and an image of how this exact model looks like after being translated to this angle. So it's not hard to collect such data. It's not hard to fine-tune diffusion model to work with such data. And with this synthetic data, we can obtain a model that takes single image as an input, along with an angle that describes the coordinates the translation of the model, and we can use this fine-tuned diffusion model as a model used for training signal in text to 3D. In fact, this solution solves two problems at the same time. It solves Janus problem by providing us with explicit control over the rotation of an object, and it also tackles low sample diversity, because now the diffusion model is trained to produce the exact same model that you've given as an input, but from a new angle. So how does it work? These are the examples of model outputs when you give an image and give an output. And then you can also run a text to 3D algorithm to produce some outputs. Some examples of outputs are given here. This is a work called 0123, which I believe was published this spring. And after this work, the development started So the developments became even more rapid. So this is a video of how this model looks like. And another team improved upon this solution with a more sophisticated pipeline with a good engineering work. And they ended up obtaining models that look even more realistic. These are examples produced by a paper that was published this summer. And of course, in October, there are even more improvements that show even more impressive results, which you can Google. The naming is similar in those papers, but I really struggle to keep up here. So let's look at the examples. We have an image of a dragon. And this is a model that we generate. These are the normal maps, which are quite impressive. So the models in motion look like this. All of them look quite coherent, maybe except for the drums in the bottom right, but other models look nice. Okay, this wraps up my presentation. A few takeaways from the second part of the talk. So it's quite surprising that pre-trained text-to-image models, in fact, can solve text to 3D. And the key idea behind this solution is that we can leverage text to 2D models to optimize more complicated processes with indirect measurements. And the only thing that we have to be sure about is that the process that generates our observations is differentiable, which is true for nerve rendering procedure. And another takeaway, which I find quite inspiring, that even if some of your models have problems which seem fundamental, some out-of-the-box thinking approaches can solve the problems quite easily, which is cool. Thank you. Yeah, I did.
This kind of problem is internally so-called ill-posed problem.
Mm-hmm.
It means that when you try to approximate back an argument of a function, the approximated function diverges. This is the problem. You cannot avoid it. How do you overcome this issue?
So I've talked about inverse problems in the second part of the talk, but also I've talked about inverse problems in the first part of the talk, because the first part of the talk was a little bit more related to inverse problems. And the fact is that, yes, indeed, the problems we're working with are ill-posed. This is an issue in novel view synthesis. In text to 3D, the problems are even more exotic and hard to interpret. And the only fact we're sure about right now is that somehow these approaches work, and they tend to work most of the time. But we do not really know yet how to tackle the fact that they're ill-posed. This is well, of course, these solutions, they use some sort of regularizations. Yeah. First of all, the Adam algorithm that is used for optimization these days, it adds L2 regularization by default, and it's already in the system. Okay, I'll repeat the question because probably the online viewers can't hear the question. The question was the following: in our nerf models, I define density as a value from 0 to plus infinity. Are there any numerical issues arising due to high ranges of density for dense surfaces? Well, this is a good question. Thank you. So, from my experience, you cannot really train density as it is. There are several tricks that are required to make training procedure a little bit more stable. So usually the output of a function parameterizing density is a real value, and then you process it with soft plus, which maps you to 0 plus infinity interval in a nice manner without exploding gradients. But this is not sufficient because the rendering algorithm takes into account step size of our ray grid, and usually you define the activation function of a density function as soft plus multiplied by some scalar that is used to tackle the problem with output scale, and also you add some bias term inside of soft plus to make optimization also smoother. There are heuristics that are being used. Okay, thank you.